Let's take a look at example 2 of 13.8. We're asked to determine the relative extrema of f of x comma y equals 1 minus x squared plus y squared raised to the 1/3 power. To begin, we want to start by finding our critical numbers, or I should say our critical points. So we need the partial derivative in the x and the y variable. Let's go ahead and calculate f partial x. The partial derivative of f with respect to x is going to be equal to the derivative of the constant 1 is 0. We would bring the 1/3 power down, reduce the power by 1. 1/3 minus 1 is negative 2/3. Leave the inside function alone. And then from the chain rule, we need to multiply by the derivative of the inside function with respect to the x variable, and that should be equal to 2x. So fx of x comma y is going to be equal to negative 2x all over 3 times the quantity x squared plus y squared raised to the 2/3 power. We now want to go ahead and find the partial with respect to y. The partial of f with respect to y, it's going to be almost essentially the same type of work, but the result will give us negative 2y divided by 3 parentheses x squared plus y squared to the 2/3 power. In order to find our critical points, they can occur at one of two places. There's the places where both the partial with respect to x and the partial with respect to y are simultaneously 0. So we want to set each of these partials equal to 0 and solve. We have negative 2x divided by 3 times x squared plus y squared raised to the 2/3 power. We want to see where this is equal to 0. It's a classic equation that has fractions in it. Multiply both sides by the denominator. To clear the fractions, you would get negative 2x equal to 0, which would produce x equal to 0. If we set the partial of f with respect to y equal to 0, you would work through the same type of algebra, and we would find that y would also have to be equal to 0. So when is both the partial with respect to x and the partial with respect to y equal to 0? What happens when x is 0 and y is also 0, which gives us one critical point, which is the ordered pair 0, 0. Let's now look at the critical points of the second type. These would occur where either f of x is equal to 0, where f of x is undefined. So where the partial with respect to x of f is undefined, or where the partial of f with respect to y is undefined. Again, this is a or statement, it's not an and. These two partials, if you look at them, they both share the same common denominator. So they're both going to happen to be undefined whenever 3 times x squared plus y squared to the 2/3 power equals to 0. You would divide both sides by 3. We would get x squared plus y squared to the 2/3 equals to 0. To get rid of the 2/3 power, you could raise both sides of the equation to the reciprocal power 3/2. That would give us x squared plus y squared equals to 0. And x squared plus y squared equals to 0 will only ever occur when both x and y are simultaneously equal to 0. So it produces the same ordered pair that we had from our first type. We can go ahead now and compute the value of f at this ordered pair. If we compute f of 0, 0, this is going to be 1 minus 0 squared plus 0 squared raised to the 1/3, which is equal to 1. In order to determine whether or not this is going to be a relative minimum or a relative maximum, or perhaps neither, we can do a little bit of analysis on the function. If we look at the way in which f of x is constructed, it's 1 minus x squared plus y squared to the 1/3 power. Well, as a quantity, x squared plus y squared is always going to be non-negative, meaning it'll be at least 0 or positive. And then when you take the 1/3 power, which is equivalent to the cube root, that will still produce a positive result. So essentially we have 1, and we're subtracting at least something that's going to be 0 or more. When x or y is different from 0, this quantity will be a positive value, and the result we will get will be smaller than 1. The largest value that f of x comma y can ever take on, it's going to be that value of 1, precisely when x and y are both 0. So it turns out that this gives us a maximum. So at our critical point this time, we actually get a maximum. It was kind of convenient that the form of the function allowed us to do a pretty easy analysis just by considering computational concerns. What we're going to look at next is a test that'll kind of streamline this process and help us to determine at each critical point whether or not we get a maximum, a minimum, or perhaps neither.